Hello, everyone. Good afternoon. Welcome to the lecture number 10 of our quantum computers course. Do you see my screen and do you hear me well? Let me ask.
Yes, Professor.
Awesome. Thank you very much. So let us, as usual, let us start with the recap of what we've done last time, lecture number 9. So lecture 9, we started from the general discussion about quantum algorithms, what they are, how they, like, in general, how they work, the purpose, and the main physical concepts lying behind the quantum algorithms. So I underscore the importance of these three key points, right? The quantum superposition first. So we must be able to generate a qubit in a superposition state. Then we need quantum entanglement, which is more interesting property of interaction of two qubits and generation of an entangled state, like Bell state in our system. And another key component is quantum interference. So quantum interference is the main point relating to quantum algorithms. Okay, because these two pretty much the same. So we always generate qubits in a superposition. We always entangle them with two qubit gates like C0 gates and so on. And this quantum interference, basically the purpose of an algorithm is to tailor the quantum interference in a way to get the desired or correct answer. Okay, so of course we don't know what is the correct answer, so we need to design the algorithm how to solve the problem, the particular problem. This is the typical structure of pretty much any quantum algorithm. So as you can see, we always start from the qubits in the zero state, which is the ground state. Then we apply a layer of Hadamard gates, which create the perfect balanced superposition of basis states, right? So we open up the coherence, let's say. Then we have something in the middle, denoted by this function f, which we control, which we program, right? So it's a set of quantum gates that that affect, control all the qubits in a way to enable this interference between all the qubits so that the answer appears on one of the output or number of output qubits. Okay. And there is, of course, another layer of Hadamard's to close the coherence and enable the interference. Okay. So in some sense, it is very close to the light that travels between two, for example, metallic, semi-transparent metallic surfaces, or between two pieces of glass, for example, right? The light travels back and forth, bounce from one layer, from another layer, and interfere with itself. And this interference, this interaction leads to the creation of some optical response, for example, right? One can find another example like this from antenna, from microwave technologies, like microstrip resonator, for example, right? Where also the current bounce from the ends interfere with itself and creates these standing waves. So it's this picture has like a like similarity to that wave physics, because wave physics is all about interference. And quantum computer also almost all about quantum interference and the way how we manage the quantum interference. So the way we manage the quantum interference is exactly how a quantum algorithm works. All right, so the first quantum algorithm we started was the quantum teleportation algorithm. At this point, we say that there is a theorem, an important theorem, which is called no cloning theorem. This is basically a statement that we cannot clone, we cannot save the quantum state by measuring the state, because any act of measurement leads to destroying of the quantum state, because of this fragility of the quantum state. So no cloning. But then if I need to transfer the quantum states to another system, to another place, to another person, how I do so? I do that using the quantum algorithm protocol, or quantum teleportation algorithm. The way we do so is called shared randomness. So the shared randomness is based on generation of a entangled state, okay, like this one. So this is not a Bell state, because for the Bell state, alpha equals to beta and equals to 1 over square root of 2, right? So this is a just shared entangled state. And from this state, in this tensor product 0, 0 and tensor product 1, 1, the first element belongs to one person. We call this person Alice. Another element stands for the state of a second qubit, which belongs to a person. We name the person Bob. Okay, Alice and Bob. And for example, if Alice measures her qubit in the 0 state, then she automatically knows that the Bob's qubit is also in the 0 state. Likewise, if the first qubit was in the state 1, the Bob's qubit also will be in the state 1. So somehow Alice can control the probability distribution of the qubit at the Bob side, regardless of the distance between Alice and Bob. This is very interesting phenomenon. It's called quantum non-locality. It doesn't break any physical law, physical concepts like the Einstein's the ultimo how to say the maximum velocity of the information transfer, right, which is the speed of light, and so on. So it's a completely quantum phenomenon which doesn't have any similarity in the classical physics, which was like very established and confirmed with hundreds of different experiments across platforms, from optics to microwave quantum and so on. So it's very, very established principle. Okay, so what we do with this shared randomness, the Alice and Bob, they share the qubits, and then Alice measures her qubit, but not in the 0-1 basis, but instead she applies the Hadamard to change the basis from 0-1 to plus minus. Okay, and she measures the qubit, her qubit, in the plus minus basis. And this results in a teleportation of a quantum state to Bob. And there are two possibilities here. First is to teleport the correct state, or there is a possibility to teleport the state which differs from the correct one by this minus sign. So at this point, Alice calls Bob through the classical communication channel and says, "Oh, Bob, you need to apply some gate to fix this minus here, or to correct it." And Bob applies a gate to correct this minus, and that's it. So he gets the correct state. So either state is completely random. You cannot predict in any way. It is 50% probability. 50% probability of transferring the teleporting the correct answer, the correct state, sorry, and 50% of teleporting the state which is almost the one we need, just need to correct it. Okay, so we cannot predict that, and in order to correct it, we need to send a signal through the classical communication channel. So it's not, you cannot send information faster than the speed of the classical communication channel using this approach. Okay, then we we discussed also the more classical or more practical quantum teleportation using Qiskit. So we discussed the circuit step by step. So I encourage you to go through this part once again. So basically, the circuit, the final circuit looks like this, right? Again, the first two qubits belong to Alice. So Alice, she has one qubit. It's her own qubit initially, and she also gets another qubit, second qubit, which she entangle with the Bob qubit, which is number 3 here. Then she entangles her qubit that she shares with Bob. She entangles it to her own qubit, then applies Hadamard and measures both of her qubits. This is how it works in practical realization. Okay, so this is the teleportation. I encourage you to read about this. We also discussed this algorithm using SymPy quantum. Okay, so here the procedure is exactly the same. But this SymPy quantum probably more convenient in terms of you have access to each part here, so you basically can write all these states, operators. You can transform them to the matrix form. So I find this library particularly useful. What else? Yeah, and we started discussing the Grover search algorithm. So So probably the angle I tried to present this part was not that good, because I realized that before this part, we can first discuss a more like a simplified picture. I read some materials how people usually teach this part. So all this is totally correct, but now I suggest that we revisit the Grover's search algorithm, and we start from a little bit more simplified picture, okay? And this is where we come to the lecture 10. So again, as usual, I import some of these libraries that I'm gonna use today. And also, I also put this lecture 12 from from the previous quantum computing course, where I discussed the math behind these algorithms like in more detail. So if you are interested in going and learning the math behind, I refer you to this course, to this lecture. Okay, so in this lecture, I decided to sacrifice the math, like mathematical side, in favor the presenting maybe more information and putting the complex things in a more accessible way. Okay. So Grover search algorithm. I remind you that the purpose of the Grover search algorithm. So this algorithm intends basically to improve, to speed up the blind search in a non-structured structured a list of elements. So this list of elements can be the phone numbers, it can be words, it can be some links on internet, it can be a list of names, whatever. And like classically, if you have a list of n capital elements, okay, how many times we need to call the list before we finally locate the element of our interest? In average, it's going to be something around n over 2, right? Because sometimes it's possible to locate the element like almost immediately after we started the search. Sometimes we need to run the search until the end of the list. In the average, is going to be n over 2. And for sure, it scales as a factor of n. So the more elements in your list, more calls you need to do to finally find the element in the list. And in order to give you before that, so the Grover's algorithm promises to improve this blind search. And here, using this algorithm, the number of calls to the list scales as a square root of n. So instead of n, you get square root of n, which is like a big improvement. And in order to give you an idea how this complexity, right, scales with the number of elements, I draw these two functions here. This is the result. So n, the blue curve is just n. right? So it's linear function. Square root of n is presented in green, and you can see the big difference even for 10 elements. For 10 elements, this search algorithm is useless, right? We need to search in the list of much more elements, maybe 10,000 or even more. And in this case, the improvement in the speed up is terrific, right? So yeah, so if we have such algorithm, we could greatly improve, for example, our internet search, some other real application areas. How this algorithm work? How does this algorithm work? So the key point here is so-called the amplitude amplification. Okay. So let us look at this balanced superposition state of two qubit system. Okay, 1/2 0 0 plus 1/2 0 1, 1/2 1 2, 1/2 1 1. So it's a perfect balanced superposition of basis states. I can amplify some of these states. For an example of this last element. So what does it mean to amplify? Amplification means increase of the probability of finding the state in experiment. Okay, so if I measure my system in this state, here I will get 25% for each of these states. With 25% probability, I get any of these states, right? However, if I amplify one of the states, like this one, meaning that I increase the probability amplitude in favor of the other amplitudes here, right? So I make other amplitudes smaller and the desired one larger. Of course, I cannot completely get rid of other states, so this cannot be perfectly one, but amplifying the state, we can unboundedly go up to one. Okay, so for example, in this example, this element here is already very close to one. So this is amplified state. How we amplify states in quantum? And this idea lies behind this search algorithm. So let's suppose we start with the balanced superposition of two qubits, like shown here. Here we have this on the axis y, we have probability amplitudes, right? And in this initial state, we have 1/2 for all of them. So what I do next, I inverse one of these states. Inversion here, because I remind you, this is the complex valued numbers, right? And inversion here means simply changing the sign. So conversion this plus into minus. Okay, so all other elements with plus, and the last one, the one we want to amplify, comes with minus. Okay, so this can be done with some sort of a matrix. Okay, what is the next? The next step is to find the average of all these states. So in this particular case, the average is 1/4, right? And it's located here in the middle. And then the last step is to flip all the states, like reflect all the states across this 1/4 line here. And obviously, all three states will turn into 0, and the last one will be amplified. So it will convert from -1/2 up to 1/2. Okay, so now instead of, so in fact it's going to be even 1. So for the last one it's going to be upper, it's going to be almost 1. Yeah, so this is how amplification of a state can work. And now if each of these basis states encode some elements, each particular state encodes a unique element from the list, non-structured list. In this case, this is the useless list of 4 elements. Okay, but applying this procedure, this protocol, we can find the element we need. And what's more important, we can find this element in a single run, because this inversion, this average, and this reflection is conducted through matrix product. Okay, so it's just operator. I apply 2 different operators, and I get this amplified state. So now, instead of calling to this list like 4 times to locate this element which is encoded to the state 1/1, okay, I need to run this search just once, apply 2 operators, and run this code just once. And this way I will find my element like immediately. Effectively, it means that we create a superposition, the perfect balanced superposition from 2 qubits. Okay, so we have 4 possibilities in the beginning, and then we work with all 4 components like simultaneously, and then we get the result. Now imagine if we have a system of 3 qubits, for example. Then we would have 8 elements, and we can encode 8 elements of a list. Okay, in some list. And again, we can run this code just once to find out the basis vector that belongs to the element v after. And now, if you continue this logic, if you apply this procedure to the system of 100 qubits, for example, then you would be able to to search for an element just with one call to the system of a huge amount of elements, over 2 to the power of 100, right? So it's a huge number. This number is the larger number that is greater than the number of particles in the visible universe. So it's a great number, and still you can find the particle in the system with just one single run of this code. So all right, so this is more or less how the Grover's algorithm works in a nutshell, right? So now a little bit about terminology. So this first operation, this operator that conducts this inversion, is called the oracle function or oracle operator. Why? Because oracle function is designed in a way to flip the state of interest. For example, similarly, we could search for another element, this 0, 1 element here, right? Then this oracle will be designed to the search for the specific element. And then the oracle would flip this second state in this example, and so on. So this is the oracle function. Typically, oracle function is a binary function that gets some zeros and ones in the input and returns 0 or 1 or true or false in the output. Okay, so this binary logic function. Another function that performs this flip of the states is called rotation function or rotation operator, or alternatively amplification operator or amplification function. Okay, few words about the oracle. So let us define the function, the simplest oracle that's purpose is to search for particular element in a non-structured list, and let's say this element is 5. Okay, so I define the function in a standard way. I give the winner. This is the element we after, and then if I put this input here, I will put the elements to this oracle one by one from this list. Okay, and for all elements but the winner, the oracle replies false. But if the input is correct, it returns true. Okay, so this is how this oracle function works. This is classical oracle function. So now let us just enumerate all these elements in the list and check and put these elements as an input to the oracle and print only the correct answer, right? The one we, oops, I didn't run this part, and this one. Yeah, so the oracle found the element 5 in this list here, and the index of this element is 9, and it placed on the 10th position, right? I remind you that counting starts from 0, and the oracle needed 10 calls to the list to finally locate the element. Now you can, of course, you can add more elements to the list. It can be words, it can be whatever. Still, the oracle will check all these elements one by one. So it's a blind search or brute force search, right? And finally found this winner, this element here, but it needs, for a large list, it would require a lot of time to find the element. So now let us discuss the quantum oracle. So the quantum oracle is a piece of circuit. Okay, that's why we create this quantum circuit in IBM Qiskit. This simplest circuit gonna be 2-qubit system. I give it a name oracle, and let us show the result. This is the result. As you will see, this oracle, which is nothing but the control Z gate, is exactly the oracle we need to flip the sign of the face of this element 1, 1. Okay, so I refer to this example. I need to find this element 1, 1. That's why I design, I tailor and apply this oracle, which in this case just simple control Z gate. Okay, so I encourage you to go to the lecture about the main single qubit and 2 qubit gates. We discussed how this gate worked, and what it basically does, it flips the sign based on the on the state of the control qubit. Okay, so this is the oracle for our quantum circuit. We designed this oracle to find a particular element, to find a particular basis vector that encodes a particular element from a list. Okay. So now we need to start the Grover circuit. So we create a quantum circuit with 2 quantum and 2 classical registers. We put Grovers, we put the Hadamars to every qubit. So we create the superposition, right? This is the layer from our generic quantum algorithm, this first layer here. So we create the superposition. So let us check that the state we created is indeed superposition using this state vector simulator. We discussed this one when we were talking about the Qiskit system. I guess that was lecture 8. And indeed, the result of this circuit, of this simple circuit, is the balanced superposition state. 1/2, 1/2, 1/2, 1/2. So now we can add this oracle we created here. I didn't mention that this before because we didn't need it, but using this function toGate, I can convert a piece of circuit into a gate. Okay, so I don't need to write this part of the code from scratch. This is the gate. I call this gate oracle. So we can now append this Grover algorithm, this circuit, with the oracle, and the result is like this. Let me quickly. Oops, I broke everything. So let me start off from over. Yeah. So now the circuit contains the oracle. So this is the generic gate that we called oracle. This is nothing but this part of the circuit here. Okay. And using this operation, we can substitute for the oracle any other type of circuit. So let us execute. Let us simulate this circuit, and we still use this state vector simulator. This is the result. So as you can see, indeed, we get this minus here, right? We started from plus in the element 1, 1, and we come to the minus at the element 1, 1. So indeed, this oracle flips the sign of the last element, which is the this state inverse, stage inverse in our algorithm. Okay, so we've got minus, and we're ready to basically realize the simplest Grover algorithm. So let us draw this circuit again. This is the circuit we start with. What else we need to amplify the particular state, the state 1, 1? We need to apply the reflection operator. So for this particular case, the reflection operator is reflection operator looks like this. So it's a system of two Hadamars, then two Z gates, then Control Z, and another layer of Hadamar. Okay, so this is the reflection operator. So it looks a little bit more complicated than the oracle, because the oracle is just single 2-qubit circuit, the 2-qubit gate. But the oracle is designed for different elements. The oracle is different. Okay. The reflection operator is pretty much the same for all circuits, for all algorithms. So no need to design this one, because what it does is just reflects the all states simultaneously across a particular vector. In this case, it was this vector 1/4, this averaged vector. Okay. Yeah, so this is the reflection. Again, we create the gate from this reflection circuit and append this reflection to the Grover. This is the circuit we obtain. So what we do next, we need to measure this circuit in both qubits, qubit 1, qubit 2, we measure them, and the result of the measurement goes to the classical register C. So we're ready to simulate this circuit. We cannot simulate the circuit using the previous state vector simulation, because now we have this measurement operation. That's why we need to apply this custom simulator from Qiskit Air library. So custom simulator, right? Lecture 9, we discussed what's the difference between custom simulator and other Qiskit simulators. So the custom simulator I can run on my personal computer first, and second, it takes into account the noise. So it mimics the noise and the imperfections of a quantum computer. And I put a number of shots, just one. So I run this circuit just once. No need to run it like thousands times. Okay. And the result is here. So the result is unique, only state 1, 1. And yeah, and we got this from the single call. Of course, if I put more shots to this experiment, all 100 shots will end at the state 1, 1. So it indicates that the oracle with reflection applied just once is enough to find the particular element of interest. Yeah, so just one call. and one application of oracle and reflection. Do you have any questions about this part? Not for now. Okay. Yeah. So, if no questions, let's discuss this general algorithm. Okay. So, what we gonna discuss now is essentially this picture, but put on in a more rigorous form, rigorous way, and we represent the states by vectors in the Hilbert space. Okay. So let's denote by omega vector is the vector we are looking for. The omega here, I mean, it represents the Wiener, right? It looks like W, so it's like Wiener vector, the vector that encodes the element we're searching in our list. So we know this vector, okay? So we know this vector, we looking for this vector in a huge list of other vectors, but we know this vector. And we know this vector, and hence we can create another vector, which is orthogonal to the vector omega, okay? Just by applying some operator that rotates this vector by angle of 90 degrees. Okay. So S prime vector is the vector that is orthogonal to the vector omega. This picture represents this vector omega and vector S prime orthogonal as vectors in the Hilbert space. So now the protocol, the algorithm is as follows. So at initial state, we create the perfect superposition state, balanced superposition state, the state S. This state is created by applying this first layer of Hadamard's. So after this point, after this layer of Hadamard's, all qubits are in the superposition state, and this state is represented by the state S. Okay, so next we apply the oracle, which flips this vector S or rotates this vector S around the state S prime by angle of theta over 2. Okay, so after this we got this new vector here denoted by u omega s, and so this is the oracle operator. Next we apply another operator that rotates this vector u omega s around the initial state S by the same angle theta. And as a result of this two operations, we get a new vector u omega s. And well, us operator is the amplifier or reflection operator. And the main point here is that you see that this vector gets closer to the state we're searching for. It's not perfectly aligned with this state, but it gets closer. This implies that if we repeat this operation several times, like I start from this vector here, then I rotate this vector around this vector S prime I will get some vector pointing downward. And then rotate it again around vector S, I will get another vector which is even closer to the vector omega. And repeating this operation several times, I will get the vector like aligning almost perfectly with the vector of our interest. This is the schematic presentation of this idea. Okay, so you remember this notation here by this line and n on top. I indicate that this circuit contains some n qubits. We start from 0 state. We apply the Hadamard's to all of the qubits, right? Get this superposition balanced state, and then apply oracle and reflection operator, and we repeat this this pair like iteratively several times, namely r times. And this pair is called Grover's iteration. And this number of pairs of the number of Grover's iteration must be or almost equal to the square root of n, where n small is the number of basis vectors, right? N capital is the number of qubits, and this number of qubits encodes 2 to the power of n capital basis states. So R must be slightly less. In fact, this formula also contains a prefactor here, which is less than 1. So this number of iterations is slightly less than square root of n. So basically, what you need to round up this this number to the lower digit. For example, in our case of 2 qubits and 4 basis vectors, this formula would give square root of 4, which is 2, right? And in fact, if I apply this Grover's iteration like second time, I will get the same result, because already this vector in my example here gets perfectly at the state 1,1. Unfortunately, it doesn't work perfect always, and in reality, this vector cannot get perfectly to the vector omega. So they can never lie on the same line and point in the same direction. What actually happens is when you apply these iterations like square root of n minus 1 times or square root of n times, you get this vector very close to the vector omega. But when you apply this iteration another times, like square root of plus 1 iteration, you get this vector on the other side. And if you continue applying, you will move away from the vector of interest. So when you apply the search algorithm, you need to first figure out this number of iterations. So this is it about the Grover's algorithm. Do you guys have any questions? All right, so then let us continue to another algorithm, which is called Deutsch algorithm. So this one, probably I will go not that detailed, and just show you the principles and a simple example of using this algorithm. So in fact, Deutsch's algorithm was the very first pioneering algorithm in quantum computing. That's why this one is particularly like important to discuss. In the same time, this algorithm is, I would say, useless. It is very, very um, uh, how to say, very far from reality. Okay, so it's I'm not aware of any applications of this algorithm, except for just one application, which is benchmarking the quantum computers. Okay, so this is the algorithm you can run on a machine to evaluate it, like to test it and to see like whether your system works good or not. Because the idea here of using the oracle function, whether constant or balanced, is like relatively easy to implement on a quantum computer. Okay, so what is the Deutsch algorithm, and what's the problem here? So what's the problem this algorithm is supposed to solve? Again, this is very mathematical and has nothing, no applications in reality. So let us consider an oracle function. Again, the function that gets zeros and ones in input and returns 0 and 1 as the output, or true and or false in output. And now we say that there are two types of this function. One type is a constant, like if you send 0, the function returns 0. If you send 1, the function returns 1. So it's a constant function. There is another type of function, however, which is called balanced. Balanced means you flip the result. You send 0, you get 1. You send 1, you get 0. It's a constant and balanced function. There are two types of this oracle. And now the Deutsch problem, you know, the mathematicians, people who study math, they tend to create problems that have nothing in common with reality. So this is a example like that. So it's a problem. This problem says that how many calls to the function we need to do to figure out whether the function constant or balanced. Okay, so here I summarize what I just said. We have function, it gets 0, 1. For example, for one qubit system, we can have only these two options, and it returns 0 and 1. And therefore, we have 4 possible cases. When we send 0, and we have 0. If we send 1, we get 0. Then the function is constant of the first order. We can send 1, it returns 1, so it's another possibility. So it's still constant. However, if I send 0 but I get 1, this is the balanced function. So 4 possibilities here. And on average, again, we need to call several times to this function if we do classically, right? If we use classical algorithm, we call this function several times. In this case, I guess 4 times to figure out the type of the function. The function itself is pretty useless. However, you can imagine this function for yourself as a coin. Okay, so if the coin is fair, is real, it gets 2 different sides, right? That you can basically look at, recognize, and immediately see that, oh, your coin is real because the both sides are different. However, if we imagine some sort of a fake coin with the same side on both sides, right? The same picture on both sides, like tail. Then this is a fake, and the question is how many like tosses I need to do with the coin to figure out whether the coin is real or fake. So classically, it's obvious, right? I need to look at the coin 2 times from both sides, and then I decide. So Deutsch states that the same procedure can be done with less number of calls, namely something around logarithmic function of n, where n is the number of elements, number of different types of the function, and in our case n is the number of qubits. Okay, so this is the principle. So how we realize this? So in order to realize, so again we exemplify this using the Qiskit, right? So here, as a first part, we start with the 1 qubit in the state 0, and we need to flip the second qubit to the state 1. Okay. Then, like always, we apply this layer of Hadamars to create the balanced superposition of the basis states, because we're gonna work with all of them simultaneously in the single run, right? Then we need to design the oracle. In this case, the oracle is simple. It's either constant or balanced function. So if the function is balanced, we apply this control X gate. Okay, so at this point, I assume I don't know this what is there. It is nothing there, or the control X gate there. I don't know. So I don't know whether my oracle is constant or balanced. I don't know this part. This part is like black box. I can't look at that inside. So it's just a black box with 2 inputs, 2 outputs. And the Deutsch algorithm claims that we can run this simulation once to figure out the types of the function. Basically, to figure out what is in the box, what kind of function lies in the box. So following the procedure, after this one, I apply another Hadamard So after my black box, I apply the Hadamard before the measurement, and again measure this the first qubit in the system in the plus minus in the plus minus basis, because after the Hadamard. Let us let us execute this circuit again. This is just one run here, and the result is this one. So after one run, we get this state 0, 0, 1. So the qubit, the second qubit, is in the state 1, and the qubit 1 in the state 0, which is the indication that the function that is covered in this black box in the center is the balanced function. Okay, and if I add more shots to this, I always get the same. So this is rather trivial, but so if you look at this circuit, you might wonder that this is rather trivial circuit. But the key point here to understand that I don't know what is in the middle. I don't know what is the function in the middle. Okay, if I change this oracle by another function, for example, remove this one, so my function will be constant. The answer will be different, and also will be the answer will be like the same regardless of the number of shots. And we will get 1 here, which means the state is the constant, or probably not in this case. Maybe for the constant I need another oracle. Anyway, so this is the way how this Deutsch algorithm works. Do you have any questions at this point, at this moment? Very good. Another type of algorithm, which is generalization of the previous one to the system of n qubits, is called Deutsch JOSA algorithm. The two names of two scientists, mathematicians. Yeah, and this is just generalization of the Deutsch algorithm to a system of n qubits. So you basically need to apply n plus 1 number of qubits to run this algorithm. Again, let us just draw the circuit because we already know the parts, right? So the last one always created in the state 1. The first two, the qubits we apply the oracle to are in the state 0 initially. Then we create the perfect balance superposition of the basis states. Again, we have something like in the black box, we don't know what is there, but we know that it is the oracle. This is the logic function, but we don't know whether the function is constant or balanced. So something is there. And then in the output, again, we put this layer of Hadamards and measure the two qubits, the first one and second one, in the basis plus minus. Okay, let us simulate the circuit, and yeah, this is the result. We measure 2 qubits. The result is 1, 1. So as far as I remember, this is the case for the balanced circuit, for the balanced oracle. Yeah, so Deutsch algorithm is generalization of the Deutsch algorithm to the larger dimensions. Finally, we came to very important case. This is another algorithm, which is often, like very often, works as a part of other algorithms. This algorithm is called quantum Fourier transform algorithm. So you are electrical the most of you are electrical engineers, and you had this course on math and calculus signals. So I bet you are aware of Fourier transform and concepts like fast Fourier transform and fast Fourier transform matrix, right? So in some sense, quantum Fourier transform operates similar way. So what is Fourier transform basically? Like, say I have a signal, like in classical physics, right? Like I am radio or electrical engineer. I receive some signal. The signal is in time domain, but it's not convenient to operate with the signal in time domain. So I change the basis. I change the basis to the Fourier basis. I do Fourier transform. So I convert the temporal signal to the frequency domain. Okay, so I can represent any signal in the frequency domain, and that's very useful. Why? Because frequency domain is just the table of numbers, right? So instead of a process, instead of a like time domain function, I get a table, and then this table can be multiplied, can be I can find the mean, average, I can find all these statistical things and so on. So it's very easy to work with tables. The computer works with tables and matrices. So sometimes it's more convenient to change the basis. Okay, and the quantum Fourier transform does similar thing. So it starts from computational basis and changes the basis to so-called Fourier basis. Okay, in a while we will see how it works. So changing the basis. This, let us return to this example with the time signal versus frequency domain table. So let's say your signal is noisy, okay? But you know that this signal contains some useful information. And useful information means that you get some repeating information, like this very distant spacecrafts or satellites that can be very, very far away from the Earth or even from the solar system. They send us some information, right, about their distance, about their condition, and we receive that signal. The signal is very noisy, but the signal repeats, and the information repeats. And what I do, I transform this very noisy temporal signal to the frequency domain, and I get the table, okay? And now I can work with the table in a way like I can find the patterns in the table. For example, I can find the periodicity in the table. And so I find that periodicity, that's my signal. I remove all other elements from that matrix and do back inverse Fourier transformation. And this way I can get the useful information from the signal that was initially maybe too noisy or something. Or when you work with the images, right? You know that this fast Fourier transform, when you save an image like in this JPEG format, like a picture of your cat, right? You save this picture of your cat in a JPEG format. So this format is nothing but fast Fourier transform of the pixels of these analog functions, right? This brightness and color and so on. It saves this information to the Fourier transformed space, which is just a table, and it's much easier to save on the memory in your computer, on your cell phone. But if you need to open, like you miss your cat, you open the picture, and what it does basically, it does the inverse Fourier transformation to get your picture. So in reality, of course, it works a little bit different, but the idea is like this. So in quantum, we also use this Fourier transform as a part of other algorithms. Okay, so but it's very important piece of story, and pretty much like any papers about quantum algorithms today, they contain this Fourier transform. So we need to learn a little bit more about this. So it's we can start with yeah. So QFT is very important. That's why QFT is already inbuilt in languages, in systems like Qiskit. Contains this. Probably I don't need. Let me see. I don't need this air. So Qiskit air is already outdated. I don't need this part. So this is extra visualization probably also. So what I need to import QFT, quantum Fourier transform, from Qiskit library, circuit library. And I do this this very simple way. Okay, so it's just one function. This function is inbuilt. You just give it then the number of qubits, the name, and maybe some other parameters you can read on their website. And so yeah, this is the inbuilt function. You no need to think about what is inside. Okay, so it's just again black box with some circuit inside. But if you need to gain some insight about this quantum Fourier transform, it can be nicely done using SymPy Quantum, the library we used quite extensively in the past parts of our lecture, of our course. Okay, so in this SymPy Quantum, we have this QFT inbuilt, but I can call this. So it recognizes the operator QFT. The first element here stands for the first qubit in the circuit. The first qubit I apply QFT to, and the last one is the number of qubits in my circuit. So it recognizes it, and I can decompose this operator in the product of other operators, right? So this is the decomposed or unpiled QFT operator for 3 qubits. For a system of 4 qubits, of course, it's going to be a string like this. For more qubits, it's going to be even more complicated product of operators. But let us reduce this number. Let's put 2, for example. Oh, it gets more simple. But let us put even 1. So I can apply QFT to just 1 qubit. And what I get? I get Hadamard. So Hadamard gate is in a single qubit circuit. Hadamard gate performs the Fourier transform. Okay, so for one qubit circuit, this Fourier space, this Fourier transformation to the Fourier basis, is the basis plus minus. Pretty simple. However, this picture breaks down when I add more qubits. So I need to apply more and more operators there. So how this circuit actually looks like? So I can check for the 3 qubits, and this circuit looks like this. So you can recognize this Hadamard, this control S gate, which is the phase qubit, but now it's controlled. Okay, so T qubit, another phase gate, again controlled. And finally, we also can recognize this control Z gate in the end. So this is how it looks for the 3 qubits. What about larger systems? So if I add 1 more qubit to this quantum Fourier transform, I get a circuit like this. So you see, there is a pattern here, like this repetition of STR, and maybe if I add another one, you will see the pattern. You see this STR. So basically STR4, R5, then STR4, then ST, then S. So there is a pattern here. This is how the circuit for the quantum Fourier transform looks like. Let us go back to the case 3 qubits. And of course, if I have Fourier transform, I also have inverse Fourier transform, and we can look at the operation of the inverse Fourier transform. So this I here stands for inverse Fourier transform in the case of 3 qubits. Okay, so this is how it looks like. Of course, this Fourier transform and inverse Fourier transform are unitary operators. They are the combination of gates, but if you look at the circuit as a whole, it is a unitary operator. And if you apply quantum the QFT and then IQFT, you of course will get the initial state. So what is the DFT matrix? Right, discrete Fourier transform matrix. So if you are not familiar with the Fourier transform and fast Fourier transform and DFT matrix, that said, I encourage you to read and watch some on YouTube, because this concept is very, extremely important. Like, especially if you plan to work with data, analyzing data, if you plan to work with images, like imaging recognition, the AI models, ChatGPT, and so on. So all this is about fast Fourier transform. So I encourage you to look at this. But what is the fast Fourier transform DFT matrix in this case? So let's look at the matrix. This is the represent function allows us to convert the QFT to the matrix form. This is the matrix form, but we can notice that these elements here repeat, so we can normalize by 4 over square root of 2, right? So we just normalize this matrix, and this is what we get. So this is exactly what we know as the DFT matrix. So let us reduce the number of qubits to the just one qubit in the system, and I remove this normalization factor here. So what I get, this is perfectly Hadamard gate in the matrix form. If I have more qubits, like 5 qubits in the system, my matrix will be like big, right? So it's a 5 matrix, and my computer already got frozen. Yeah, so it's like big matrix like this. So the purpose of this matrix, again, to find the periodicity, some kind of periodicity. You see this exponential functions here, they count for the periodicity. So watch the video here or some other resources. So periodicity and the fact that quantum Fourier transform allows us to find periodicity is extremely important for the another algorithm, which is maybe the most famous algorithm. That's why I put in the last. This is called Shor's algorithm. So what is Shor's algorithm about? So Shor's algorithm states that we can factorize the large numbers, which are the product of two prime numbers in a much more feasible way. We get the exponential speed up in terms of the time we spent to find the prime numbers. Okay, so imagine we have a big number, just large number, and we need to figure out if this number can be factorized to the product of two prime numbers. As a reminder, prime number, right, is a number that is divides by itself or by one only. So prime number. And why it's important? It's important because in math, if you have a big number in math, like you can try to divide it by 2, by 3, and if you see it divides, you can then try divide by 2, by 3, by 4, and so on. So if the big number, large number, is just arbitrary number, we can factorize it by some other numbers, right? The product of some numbers. However, if we have a large number, which is a product of two prime numbers, we cannot apply this approach. We cannot divide by 2, by 3, and so on, because the prime numbers, they cannot be divided by other numbers without remainder. Okay, and in math, there is a great mathematical problem, one of the most important, like most difficult problems in math, which states that let us say the problem to find the prime numbers of some big number. Okay, it's very easy to reverse. It's very easy to multiply numbers. Any computer can multiply two prime numbers and get the result. But the inverse problem is extremely difficult. Let's say I want to multiply two prime numbers, maybe with just 20 digits in each. The computer will calculate this number like in 1 millisecond. However, if I don't know the prime numbers and want to find the, and I want to prime, I want to decompose this number into two prime numbers, it will take like literally forever. Like you can find these estimations like, oh, this number can be factorized, like, or the time needed to factorize this number exceeds the lifetime of the universe, for example. So it's even using a superpower supercomputers. Why it's so important? That's important because encryption protocols, for example, like this RSA protocol, rely on this encryption approach, this factoring the large integers, factoring large numbers. Why it's so important? Because you actually use this encryption RSA or other versions of this protocol every time, for example, you pay something using your credit card or debit card, or every time you transfer money from account to account. All these operations are encrypted using RSA. Technically, when you do the transaction, you send, your computer, your smartphone sends a first big prime number over the public channel. So everyone can receive this information and so on. However, if you don't know the second prime number, okay, you cannot you cannot solve this problem. You cannot you cannot factorize this big large integer number. So your data is protected by this complexity of this problem. But it turns out that if you convert this large number, which is presumably the product of two prime numbers, okay, if you encode these numbers into the state of a quantum computer of n qubits, and if you do the fast Fourier, or if you do the quantum Fourier transform, you will get a table, and then in that table you can find the periodicity. So you will get some periodicity in the table using classical machine. Like you analyze the table of a matrix of data, like the one we just saw here. And analyzing the data, that matrix, you figure out the periodicity. And then there is a classical algorithm, which we're not supposed to discuss here today. It's too complicated. Classical algorithm which says that, oh, I can compute this, I can solve this problem, provided that I know the periodicity. So give me periodicity, I solve the problem. The problem is that without quantum computer, we cannot calculate this periodicity factor. Using quantum computer, we can calculate periodicity using quantum Fourier transform, and then we apply classical algorithm to find out the product. So this is very important problem, and you see, it's not useful. It's rather dangerous, right? Because if someone will get this quantum computer powerful enough, which is, by the way, gonna happen in just a couple of years, with the current trend of increase of the number of qubits in our system. So just maybe 2 years ago, we had a system maybe with 60 qubits or 70 qubits, and that was like state of the art. After just maybe a couple of years, today we have computers with 1,000 qubits. And continue this growth, this development, in another couple of years, we're gonna probably double it. So it's gonna be 2,000 or more. So something like this Moore's law growth of the number of qubits also applies here. And if this trend continues, maybe in just 5 years or so, we will get a computer which will be enough to destroy our bank system. So that's extremely important to learn these algorithms and to elaborate a way how to protect our systems against the this Shor's algorithm. Okay, so this is the like very generic circuit of the Shor's algorithm. I took this circuit from a recent research paper who claimed they run this circuit on a 60 qubits, I believe, a couple of years ago. So yeah, the algorithm is presented here. I try to write down these steps one by one, but in general, again, we start from the 0 state of n qubits. This line indicates the number of qubits, right? We apply the Hadamard to all of them, so we create the superposition state to all. Then there is another qubit in which another part, another group of qubits, in which we encode the digits from our number we going to factorize. Okay. Then all these qubits from the first group and the second group are coupled through these control gates, which is the phase gate, which depends on the state of this work qubits. Okay, and then we do the quantum Fourier transform to the first group of qubits, and then measure all of them. And this way we can find the period. Here the period is called R. Find the period, and then we apply the classical algorithm to figure out the prime numbers. So today, using this algorithm, we already can factorize big numbers. These numbers still smaller than the numbers we could factorize using just a laptop, okay? However, we have a great progress here, and in a couple of years we will be, even in this paper, oh well, in this paper they had 60 qubits. It's cannot be, or almost can be, simulated using classical supercomputer, but at the same time, the factoring can be done using a just small computer. But at some point, we will be able to factor much larger numbers that cannot be tackled by, cannot be solved by classical supercomputers. Classicals, yeah. So this is the end. And yeah, for information, I encourage you to read this part. This is the link, I guess, to the IBM Qiskit, where they discuss this Shor algorithm in much more detail. Yeah, unfortunately, in this course, we don't have much time to go through all these very interesting aspects and features. This is first. Second, the area is very actively developing, like thousands of mathematicians, scientists, computer scientists develop new algorithms to be used on existing quantum computers. Just recently, few weeks ago, I saw a news like where Google promised a prize, like price of $3 million to the group who can develop a algorithm that can be run on their quantum computers, and the algorithm is supposed to do something like very practically useful. So yeah, so this area is very developing, and yeah, and this was the introduction to the area. So next couple of lectures, I believe we still have two, will be dedicated to the hardware. So you will learn about how the quantum computers actually build, what are there at the like transistor level, right? This qubit level. So this is end for today's lecture. Thank you very much. Let me stop recording and then we can discuss.